Okay, next speaker in our session is Patrick Weidman from University of Colorado. We'll talk about terminal motion of sliding spinning disks with Coulomb friction.
Good afternoon. Thank you, Andres, for inviting me to come to this very interesting session, the last of 4 workshops for Growth and Form. I would like to share with you today some results, still ongoing study of the terminal motion of sliding spinning disks with uniform Coulomb friction. This is work done originally with Chetan Malhotra, who is now in Pune, India. The results found here may have some relevance to the game of curling. However, the friction force between a curling ball and ice is certainly much more complex because it not only scrapes the ice, but it can actually melt it. So I just thought I'd throw that in here as a possible analogy. Let's see.
Curling rock actually curls the opposite direction than it would if there was Coulomb friction.
That's right.
Yeah.
All right. Here's the pier disk problem. I'm going to review the theory for this pier disk problem because I did not derive it. It was originally reported in Phys Rev letters by Farkas, Bartels, Unger, and Wolf. And Farkas in Romanian means wolf. So there are 2 wolves in this title. All right, so the question is, what is the terminal motion for a disk sliding and spinning across a smooth horizontal table? Regardless of the initial conditions, meaning both rotation and translation are imparted to the disk, the disk stops spinning and sliding at exactly the same instant. Not only that, the ratio of the linear speed to the tip velocity of the disk is always 0.653, regardless of how you initiate the motion, as long as there's both spinning and translation. All right, so here's a review of the theory by Farkas et al. There's the friction force, which is the coefficient of friction times the normal force, mg, divided by the area, times the integral over the area of the linear speed plus omega cross r, the rotational speed, divided by its absolute value. That turns out to be minus mu Fn times some function of epsilon times a unit vector along the direction of motion. The torque is minus mu Fn over pi r squared times r cross this term. That turns out to be minus mu Fn times r tau of epsilon times a unit vector vertical for rotation. So here's the normal force, and the all-important parameter here is epsilon. That's V over omega r. That could be epsilon at any time, V of t over omega of t times r. All right, Farkas, in his original paper, et al., used complete elliptic integrals of this form. They had f defined for epsilon less than or equal to 1 or greater than or equal to 1, and tau defined for epsilon less than or equal to 1 or greater than or equal to 1. I found this rather cumbersome. These are complete elliptic integrals E and K, and I didn't want to have to worry about going through epsilon 1 if a solution allowed that. So I wrote this in terms of incomplete elliptic integrals written here. So this is E and F incomplete elliptic integrals with a parameter alpha, and alpha is 4 epsilon over 1 plus epsilon quantity squared. All right, so this makes the calculations much easier. Okay, here's a review of the theory. Here's linear momentum, rotational momentum. I is the moment of inertia, m is the mass of the disk. You normalize, so V star, omega star, and T star are now non-dimensional. When you do that, you obtain a very simple equation. dv star dt star is minus f of epsilon. d omega star dt star is minus 2 tau of epsilon. And we know now what f and tau of epsilon are. All right, you can do one more trick, and this was done by Farkas et al. You let x equal minus log of omega star, and you can rewrite this as d epsilon dx equals epsilon minus f of epsilon, or 2 tau of epsilon. Let's say that that's equivalent to f of epsilon. So f of epsilon, if you plot that now for a pure disk, here's a plot of f of epsilon versus epsilon up to this value. Of course, it keeps on going. But the important thing is that it has a fixed point at epsilon 0.653. There's, of course, another fixed point here and one at infinity. But the all-important one here is if you start at some value epsilon here, your solution will be driven to this fixed point. All right, so here's an example. Let's say you have an initial angular velocity 3, an initial rotational rate 2, and you start them off and evolve them in time. You see that they both stop at exactly the same time, 3.565. All right, so let's extend this a little bit. Let's go to an annular disk. All right, so we're going to define a radius ratio. Eta is R1 over R2. If you calculate what this new f of epsilon is, it turns out to be this function here. Epsilon minus this ratio of 1 plus eta squared times f of epsilon minus eta squared f of epsilon over eta, and similarly here for tau. So you can easily plot this, and here we have to show how we define epsilon because there are two radii. So it's the tangential velocity on the outside, omega r2 over v. All right, so here are plots of f of epsilon versus epsilon for various values of eta, going from 0, which is a full disk, to 1, which is a very thin ring. All right, so if you start here for the full disk, it evolves outward to 1, and it has different crossover values, in other words, different fixed points. Those are the terminal values of the motion. So if you plot epsilon 0 as a function of eta, it goes from 0.653 for a full disk up to 1 for a very thin annular ring. And so since epsilon 0 varies between 1 and 0.653, it's finite. That means the disk will always stop, the annulus will always stop spinning and sliding at the same time, but not with a terminal value of 0.653 for a full disk, but for a range of values between 0.653 and 1. All right, so that's a simple problem to solve. All right, but here's a new phenomenon. All right, so I decided to demonstrate for somebody what would happen if I took my eyeglass case and spin it across a horizontal table. Well, as you saw there, I think it was pretty clear that the sliding stopped first and it spun to rest. Why? Because my eyeglass is curved. It has a small area of contact but a large polar moment of inertia. So the sliding stopped first, and then it just sat there with this large polar moment of inertia and spun to rest. All right, so this is the new phenomena. We need to explain the terminal motion of an eyeglass case. Can we find disk geometries which give us all three terminal motion? Remember what epsilon is. It's v, the linear velocity, over the tip speed. All right, spinning and sliding stop at the same time if epsilon 0 is finite. If it's greater than 0 or less than infinity. Sliding stops first and spin down to rest occurs if epsilon 0 is 0, and spinning stops first and it slides to rest if epsilon 0 goes to infinity. So how could we model this in the laboratory? Well, we could make a composite disk. The motivation is the eyeglass case. We want a small area of contact and a large polar moment of inertia. So how do we get that? Well, we can build two-tier disks. So we have a lower disk, and superimposed on top of the same density is a bigger disk, let's say. And we can define the radius ratio as R1 over R2, and the height ratio lambda is H1 over H2. It's very easy then, of course, to calculate the total mass of the disk for uniform density rho, and the polar moment of inertia for the combined two-tier disk is given here. So those are simple calculations. Now, if you compute what that function f of epsilon is for which you want to find the zeros, the fixed points, you get a two-parameter problem depending on both eta and lambda. So this is quite a complicated situation. However, I stumbled across the result that the normalized radius of gyration, let's call it k squared, k is the radius of gyration, its value squared is 1 over r1 squared times I over m. That turns out to be exactly this coefficient. So now, if we write this in terms of k squared, we have a one-parameter family of solutions. All right, so let's look at composite disk results starting from this curve, which is for a pure disk. And then we could increase k, and when we do, we come to a value here. K is the square root, whoops, I'm sorry. K is the square root of 2/3. All right? And then, if we decrease it, we come to some other fixed point. Decrease it more, we come to a value k equal 1/2. And so we have now 0, a finite value and several finite values, and an infinite value. So all three terminal motions are possible depending on the value of k. And k, remember, is a function of both lambda and eta, the geometry of the two-tier disk. All right, so the radius of gyration is here. The speed ratio is listed here. If epsilon 0 is infinity, then spinning stops first. If epsilon 0 is 0, sliding stops first and it spins to rest. And everywhere in between, epsilon is finite, so you get simultaneous stopping of the two motions, the rotational and translational motion. All right, so here is k on the vertical axis plotted versus epsilon 0 on the horizontal axis. And if k goes between 1/2 and the square root of 2/3, then everywhere in between epsilon 0 is finite, going from the value of 0.853, going between 0 and infinity. All right, so let's look at the situation where sliding stops first. That means k has to be greater than the square root of 2/3. So I pick k equal 3 as an example. Let's start with an initial linear speed of 2, an angular rotation rate non-dimensional of 1, and see what happens. Well, the v velocity stops at 9.798, and the omega velocity keeps rotating up to between this value t star v up to 14.656. So there's an example where sliding stops first and then it spins to rest. That's like the eyeglass case. Oops, Here's another example. Spinning stops first. That means k has to be less than 1/2. So I pick k equal 1/4, start with the initial value of v of 1, omega of 3, and you find that omega stops at 1.108, and then there's a little interim period here where it's still translating up to 1.137. So these are the two extreme examples if you build this two-tier disk appropriately. All right, so here are the contours of epsilon 0. Remember, k is the square root of epsilon 0, tau of epsilon 0 over f of epsilon 0. And here are all the values of epsilon 0 everywhere in the regime diagram, except for this blue region and the yellow region. And the blue region, epsilon 0 is 0, and then the yellow region, it's infinite. All right, so here's the transition boundaries, and now I'm going to use this to select some values to make disks and to perform an experiment. All right, so we're going to pick up, I'm going to pick lambda as 0.1 because this slices through everything. So I'm going to pick lambda as 0.1 and then this value of eta. And then the pure disk value is 1. And then there's another value I could pick for a two-tier disk that's not just a rigid pure disk, but it's a two-tier disk. And then this value, which will give me an epsilon 0 infinity. So here they all are. I'm going to make 4 disks. These two will stop spinning and sliding at the same time. This one will stop sliding and spin to rest. This will stop spinning and slide to rest. All right, so here are the two-tier disk geometries that I built. They're made out of a PVC. Lambda is 0.1 for all of them. Radius ratio here is 1.25. This has simultaneous stopping of both translational and rotational motion. This one at eta equal 0.5, lambda 0.1, sliding stops first, and then it spins to rest. And for this one with the large contact area at eta equal 2, spinning stops first, and then it slides to rest. All right, so here are the characteristics of 4 disks that I'm going to show you some data on. Here's the radius, R1, and eta is R1 over R2. So from this, you can get what R2 is. This is H1, and lambda is H1 over H2, so you can get what H2 is. Remember, I've selected lambda to always be 0.1. Here's the normalized radius of gyration, and these are the values of epsilon 0. For disk 1, it's 0. For disk 4, it's infinite. And for these two, spinning and sliding should stop at the same time. All right, so here's a typical disk, okay? And my original experiment was over a nylon cloth spread over a flat surface and stretched. I found, come in here, I'll show you some new results we're involved with right now. But I thought about why not just put a little felt bottom on these. And so you don't have to slide the solid disk over a stretched surface. You got your nice surface right here. And so this turns out to work out really good, and I'm hoping to get some data while I'm visiting here for the next couple of weeks. I'll show you on what experiment I'm going to do the data. I'm going to try to achieve the data at the end of the talk. All right, here's the experimental setup. Oops. We had an overhead camera with some lights down, some strips to mark distances. Oh, I missed this. So the camera is up here, right here, and it shines into there and reflects down. So we can capture at 100 frames a second the motion of the sliding, rotating disk, and we know its orientation by a stripe down the middle, and then we have 2 dots over here. So we can see back out the linear and rotational speeds. All right, so here are the disks. Here's a solid disk that I just showed you. Here's one with a large surface area in the bottom, another one with smaller surface area in the bottom. This one will actually stop spinning and sliding at the same time. So will this one. This one, on the other hand, will stop rotating and slide to rest. This one, you can't see the underneath, but it has a very small contact surface underneath. In fact, if you make that contact surface underneath smaller and smaller, you'll get a top. It'll just sit there and you slide. It's like sliding the top, and then it'll just rotate around a point. Okay, here's Chetan Malhotra helping me. I'm just sliding the disk, and he's sitting there to make sure I don't slide it too hard. All right, so here are some. May I have the lights lowered, please? So here's the pure disk. You know what's going to happen in that case. Now that was a little fast, so take a look. All right, so maybe that was too fast, so look at it in slow motion. I think you can see that both translation and rotation stopped at the same time. All right, so this is a composite disk which will also stop both motions at the same time, but not at the terminal value 0.653 like for a full disk. Slow motion for that one. I think you can be convinced that both motions stopped at the same time. All right, composite disk 2, real time. I think that was pretty obvious what happened. I'll show it again. And now in slow motion. So it stopped, and it's spinning to rest. And finally, the other case, I think you figured out what happened there, but let's look at it in slow motion. So it stopped spinning, and it slid to rest. All right, so here's the experimental data backed out from the movie for the pure disk. As you see, whoops. It didn't stop at exactly 0.653, but very close. There are problems about stiction that you have to worry about. When a disk flows across the surface, it can provide some stiction. Anyway, that's the data for the pure disk. And for the 2-tier disk, there's one here where epsilon goes to 0, and it is 0 for some length of time. And the other one, epsilon goes to infinity. For this one, sliding stops first and it spins to rest. And here, spinning stops first and it slides to rest. All right. How's my time doing?
16 minutes.
Huh?
16 total minutes.
16? All right.
11 plus 5.
All right. Conclusions? No, I got a little more after this. Pure disk under uniform Coulomb friction, you always have to worry about that. Because if the disk is too high and you throw it forward, it will have more force in the front than in the back, and it can actually slightly deflect if it goes for a long enough ways. And some experiments have been done on that. However, if you do have uniform Coulomb friction, it always stops spinning and sliding at the same instance with the ratio of the linear speed to the tip velocity of 0.653. Annular disks stop sliding and spinning at the same instant, but with epsilon 0 varying from the pure disk value 0.653 up to 1 as eta increases from 0 to 1, the radius ratio. A composite disk can display all three types of terminal motion depending on the normalized radius of gyration, and the three possible terminal motions of composite disks have been verified by experiment. All right, ongoing work. So when I was invited to go to ETH Zurich one summer, and I had just read this Farkas paper, and the gentleman, Yugen Magari, that invited me there, he said, okay, we're going to work on some heat transfer and convection and this and that. And I said, oh no, you got to work on this spinning disk problem. You got to read this paper. This is what we should work on. And he said, no, I invited you here. I'm paying you here. We're going to do what I invited you to do. I said, okay. But I kept throwing coins on the table in front of him and doing all kinds of things to get him excited. And nah, he couldn't do it. However, just recently, about 2 months ago, he emailed me and says, hey, you know, on your spinning disk problem, what happens if you slide it down a plane or up a plane? He got curious about it. So that motivated a collaboration. And spinning and sliding on inclined surfaces. Phi is the angle of declination. Okay, that means it's going, if phi is positive, that means you're spinning it downslope. And if I had time, I could pull up this table and we could slide some downslope.
You have time.
Okay. Okay, so here's a summary of all of what we learned up to now. It's still ongoing. Motions on sloping surfaces. The important parameter is tangent of phi divided by the coefficient of friction mu. Okay? And it divides, if you plot epsilon 0 versus that, you find three interesting regions here. But here is the all-important curve for the solutions of epsilon 0, simultaneous spinning, sliding and spinning, stopping at the same time as a function of this, up to 0.5. Now, to orient you, this is the horizontal. When phi is 0, you have a horizontal table. Okay? So here's the horizontal table result. And for phi positive, these are all downslope. And for phi negative, these are all upslope. Okay, so there are some solutions for spinning upslope and downslope. It turns out that this turning point is a saddle point node bifurcation. It's well known that if you have stability on one side, you have instability on the other side. All right, so it turns out that this branch is unstable and this branch is stable. Now, what happens here? In all of this region here, you have simultaneous stopping of both translation and rotation. In this region here, spinning stops, but it slides to rest. At this value of tan phi over mu 1, even though spinning has stopped, it slides to rest at constant velocity. It doesn't slide to rest. It slides at constant velocity. However, in this region, you have it's too steep. You have accelerated slide, so it just continues to accelerate. And there's this critical turning point value of minus 0.0804. There are no fixed point solutions beyond that. All right, so what happens beyond that? Well, you're spinning the disk up a slope, and for values of tan phi over mu between here and minus 0.0804, it stops sliding and spinning at the same time. But if you have tan phi over mu more negative, what happens? It stops spinning, slides to the top of its trajectory, turns around, and accelerates down. So there's no fixed point.
You didn't mean turns around.
Thank you.
Okay, we have time for a few questions.
Can we see the demo?
We would like to see
What?
a demo.
Can we see the demo?
Okay. Somebody help me put up a table.
Want me to tilt the table?
Mr. Chairman?
That I can do.
Which one? That one?
How high? Actually.
Whoa, 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 whoa.
It's better on top of the other.
Oh, you want to do the vertical one?
Oh,
That's
I thought
the
that's...
favorite.
No, that's good. I don't know if that's too big. Whoa.
Okay, there's a tilted table.
That, okay, let's see.
A handsome guy after all.
Let's see if this is the critical angle.
We can't see that on this side.
Oh, where's my camera?
Okay,
tilt the other way?
it stays there, right?
Yes.
So it's below critical. So that means if I slide it, could you stand near the edge and catch it in case it falls off?
Yes, excuse me. There's a request to tilt it the other way.
But this is,
Okay.
this is
Oh.
okay. You do both ways. You can do both ways.
What do you want to do?
Would you like that? Okay, fine.
What?
They want the table tilted the other way.
Oh, towards the audience.
This is a demanding crowd.
It's not difficult to do.
Well, okay, is this...
yeah.
Let's do it this
Well,
way.
that's it.
Watch out.
Yes.
The tape, whoa, 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 whoa. This is,
That's fine.
it's okay.
It's slightly tilted this way also.
Oh, we're good.
Well,
Okay,
clearly,
don't hit us.
Huh?
Please.
clearly, let's,
No.
Oh, Jane can't see. I'm sorry. God forbid.
Yeah, God forbid. Indeed.
all right.
I will stand there and make sure Jane doesn't get hit. Can't see.
Can you get up there in case it goes off the table?
It goes up.
All right, so it's clearly not moving, so it's below the critical angle. Okay, so spinning and sliding stop first. And also, downhill, it will do that. Watch out for it down there. Okay, bring it back. All right, now let's make it bigger.
Steeper?
Steeper than the critical angle.
Can I just hold it?
Higher, higher, higher.
Come on, Dan.
There. Okay.
All right.
Is that good? All right, so it should go up and come back, right? I've never done this experiment before.
No.
But it stopped.
But oh, it started to rotate.
Huh?
It started to rotate.
Oh, maybe my surface isn't perfect.
Okay.
Just a little.
Yeah, the bottom's been affected a little bit. Anyway, so that shows that it's above the critical angle. There's no fixed point. Doesn't stop sliding and spinning at the same time, but below it, go down, below it, there, hold it there. Stop spinning and sliding at the same time. And those values of V over omega R can be predicted. All right, first time I've ever done it for a sloping table. Thank you.
Oh.